Hello there, you are watching Ako Math Musings channel. My name is Alexander. Today's topic is plane with spaces, hypo operations. We will be like this small guy looking into the hole for the stairs with a ladder that goes down and ladder that goes up was considered in previous video where we consider hyper operations. So let's move on for the next slide. Our agenda for today is consistent from these steps. First we go from hyper operations to hypo operations. Hypo, yeah. Then we will consider some basic examples how to compute with an operation that precedes plus operation. Why it's called counting zeros will be clear on that slide. Then we will consider identity elements for these hypo operations. We'll consider dual hypo operation for the operation preceding plus. We'll consider distributive law. And finally we'll consider where the one of them is used, the tilde operation. So let's go here. So in the previous video we already considered this ladder. I just want to draw it again for visual representation. So we start from plus and multiply, then we introduced triangle, we introduced square, and we showed that we can go on further and further. And we also considered that all these consecutive operations, the pairs, they create algebraic structure that are similar to each other. From this we figured out that if this space have neighbor on the right and neighbor on the left, then similar to each space has to have also neighbor to the right and neighbor to the left. But so far we don't know what's the neighbor on the left side. So this space is the topic of today's video. This operation that is here, this one, I called it tilde operation on the previous video. And we will go one step further, consider another one. This one will be denoted with a sharp operation. So we know how we go in this direction, and we will just write a formula in a second here. We inferred it in the previous video. So let's see what it was. It was something like A triangle B is equal to 2 log 2A multiply log 2B. So you see that we expressed triangle operation in terms of multiplication operation. And we also talked about the recursive definition. So we could use the same formula and, let's say, take square operation and define it in terms of triangle operation. And we could also go the other way. We could understand it as a multiplication operation, define it in terms of plus operation. And plus operation could be defined in terms of tilde operation. So this sequence of operations goes up and it goes down. And let me write this expression here on the top. I will take from this equation, I will take log from both sides, and I will write it this way: log A triangle B equal log A multiplied by log B. Okay, so something similar we want to get for the opposite row here. Let's see how we can do it. Basically we already have this recursive formula here that we can use we need just to flip it. And in order to flip it, let's do a small inference. Take log 2 from both sides. And then let's just make a replacement. So a we will replace on 2 to the power a, and b, let's replace it to 2 to the power b. Now for capital A and B, what we get is that a multiplied by b will be equal log 2 and then 2 to the power a triangle 2 to the power b. Okay, and this is the expression that we are looking for. If we just delete this portion that we use temporarily, let's look at this in more details. So here we have multiplication operation defined in terms of triangle operation. We can define same way, we can define plus operation in terms of multiplication operation. We can define tilde operation in terms of plus operation. And opposite, we can define triangular operation in terms of square. We can and go up and down in this ladder. So now, if I take from this expression exponent from both sides, and by exponent I will not only mean e to the power something, but it could be exponent with arbitrary base. It could be like, if I write exp2, it means something like 2 to the power something. Just a small change of notation for better visual symmetry of formulas. So if I take exp from both sides of this final bottom left equation, what I get? I will get that exponent of a multiplied by b is equal to exponent of a triangle exponent of b. Now look at these two formulas. This one and this one. Oops. They are very nice, beautiful formulas, symmetric. One is letting us go up the ladder, the other is enable us to go down in this ladder. I want to show another graphical representation of what is going on here, just for better visual perception. Let's say what happens in the formula, the first formula, is that we have two spaces. One space is a space of, let's say, plus operation, and this space is a space of multiplication operation. So what does it mean that we define multiplication operation in terms of plus? This is what happens when we go up the ladder. So it means that if we have some two elements here in the space of multiplication operation, we want to define what does it mean to multiply them. We first map them here. here in the space of plus we can take them, two of them, and compute what is a plus of these two. For example, this dot is a plus. And then we take this dot and we map it back here. And by definition we consider that this new dot is a result of multiplication. So the mapping here will be, we know that multiplication is a sum in log space. So to get in sum in plus space we need to take log. So this mapping is implemented by log. And the opposite mapping is implemented with exponentiation. And this is expressed in formula on the top left. Similar plot will be on the bottom, but we will have the opposite errors. So if we have plus here and we have space here with multiplication, what happens is the opposite. We know how to multiply elements and we want to define plus. So if we have two elements here in plus space, we have to map them here. Then we can multiply them because we know how to multiply them. We get new element. Now we map it back here. And we by definition consider this new element as the sum of previous two. So here the mapping for from plus to multiplication will be exp. And mapping back will be log. Okay, so these are two different representations. Finally, I want to recall that this definition is recursive. It means that, for example, let's say this one, square operation, it can be defined in terms of triangle, but triangle is defined in terms of multiplication, so square can be defined in terms of multiplication and in terms of plus, etc., etc. So this recursive definition built some sort of tower in a formula, and I just want to show this tower for both upward move and downward move. So if we have a square b, you can recall from previous video that we will have something like 2 to the power 2 to the power 2 and then triple log. And because that's triple, it means we arrive at plus operation at the end. This is sort of recursive tower that we can build. And when we go down, let's see what happens when we go down. Let's say we want to take, let me take another color. We take this sharp, we can similarly express it in, let's say we want to express it in terms of multiplication. So it's again 3 layers, and that means that sharp A sharp B will be equal powering exponentiation will be replaced with log, and log will be replaced with exponentiation. So we have triple log and here we will have powers, and then we arrive at multiplication, so we have to multiply this. Okay, So these are two expressions that show how the recursion work. We'll add them here. Now I think we can go to the next slide. So let's take this operation that precedes plus. It is tilde operation. Let's do some arithmetic with it. 0 tilde 0. It's log 2 to the power 0 plus 2 to the power 0. So it's obviously 1. Next, this one, log 2, 2 to the power 1, 2 to the power 0. This is 3 in parentheses, so it is log 2, 3. I want to notice that this is log 2, 2. Now 1 tilde 1, log 2, 2 to the power 1 plus 2, 2. It's 4 inside, it means it's equal to. It equal to log 2, 4. 2 tilde 2. Let's see. It is 3. So if you notice, what happens here is that we count number of zeros. Tilde operation use 0 as let's go back to plus operation. For plus, the quant, the minimal unit that we sum is 1. 1 plus 1 plus 1. That's how we count objects. One object is 1. For operation of tilde operation, that quant, that unit that we count is 0. And we also count it in log space. So this can explain what we have 2 zeros, we have 3 zeros, we have 4 zeros, we have 8 zeros here, log to 8. Here we have 8 zeros, etc. And also another pattern that we can see here is that we can basically express it as n plus 1. So n tilde n is equal n plus 1. Okay, so for example, if we have 5 zeros with a tilde between, we will get log 2. Here I should write 2 to the power 0 5 times. Log to 5, so 5 zeros here. Okay, so this way you can count any arbitrary integer numbers basically. A more complicated topic is identity elements. So let's see what we can figure out here. So if I have a element, I want to tilde it with the identity element. There is no notation for identity element of tilde, so I will use a generic one, e with tilde at the bottom. That's identity element for tilde operation. Log 2, basically base doesn't matter, let's say log 2. 2 to the power a plus 2 to the power e tilde. We want this, because that's identity, we want this to be equal to a. In order for it to be equal to a, we need this guy to be equal to 0, right? And 0, just recall that it's identity element for operation plus. So let's put it down. We want 2 to the power e tilde equal e plus. Let's look like some expression that can be generalized, but before we do that, let's see if we can solve this equation. So you can potentially think that e tilde is minus infinity, because then 2 to the power minus infinity equal to 0. And this is kind of what we want. So what is minus infinity here? We took it from our classical considerations in mathematics, right? It has some notion of minus infinity. It defines specific rules how minus infinity behaves. And one of those rules is that if we power 2 to this minus infinity, we get 0. But in our system, in our ladder of algebras, we didn't introduce minus infinity yet. The only thing that we need right now is this equation to be true. And for this, we do not necessarily need minus infinity. But let's stick with minus infinity. Let's see what are the problems with it. Let's now consider a sharp, E sharp. Okay. This is logarithm 2 to the power a tilde 2 to the power E sharp. And we want this to be equal to a, because that's the identity. E sharp is identity. In order to achieve this guy has to be what? It has to be equal to identity element of tilde. Let's put it down here. 2 to the power E sharp has to be E tilde. Now, if we have E tilde infinity, we need to solve equation E sharp as power of 2 should be equal minus infinity. Clearly we stuck. If we use minus infinity in classical sense, then we stuck with this equation and we cannot solve it. There is no E sharp such that 2 in its power will be minus infinity. So we need to understand here that minus infinity basically, even in classical mathematics, it's a special symbol. It's not a quantity. It's a special number that is given specific properties, specific attributes, specific behavior when it's participate in arithmetic operations. So it is an extension of a basic set of numbers, maybe natural numbers, for example. But here, the only property that we use for this minus infinity, as I said, is this one. So the only property that we need from E sharp is this one. So we can extend our system of algebras and say we don't use this like notation. No. This is not what we are going to use. We just agree that E tilde is a new number in our system with this property. E sharp is a new number, new element in our system of ladder of algebras that possess this property. Okay? And why it's a weird number. So if we just let's have a ladder of these identity elements now. So we know that we take exponent of E plus, for example, E to the power 0 or 2 to the power 0. We get 1. So we have something like 2 to the power 0 equal 1. That's from classical mathematics. But we often hear from books, from teachers, that this is by definition. There is no actually explanation or computation like 2 to the power 0. 2 to the power n is clear. That's by definition means take 2n times and multiply it, right? But 2 to the power 0 is different. We just say by definition, if I take 2 to the power 0, I get 1. So here, what we do with E tilde and E sharp is not different from that by definition. Okay, so do not be scared with this arbitrary kind of definitions. So let's just look at a ladder that we already used in classical mathematics. It's that exponent of E plus is E multiply, right? Because it's kind of 1 here. Exponent of E star, if we consider base 2, it will be equal to 2. 2 to the power 1 is equal to, but 2 we know it's identity element for triangular operation. So we can continue in this direction, but we can write things on top as well. So to get E plus, we just found that we need E tilde to be exponentiated, and so on. We can say that exponent of E sharp is actually E tilde. Okay, this is the ladder of identity elements, and for some of these elements we have just notation. For example, E plus is special notation 0, E multiply is special notation 1, and here we had special notation like 2, and here we may say that this is 4, but here we don't have a special notation, so we will just use E tilde, and so forth. And if we take logarithm of this, let me just somehow make it a bit smaller. We can take logarithm of this and we can get something like E sharp is equal log of E tilde, and E plus is log of E, sorry, not E plus here, E tilde is log of E plus. Here you can temporarily think of this as like minus infinity is logarithm of 0. Okay, but now we can go further. E plus is log, no, that's not further. E plus is logarithm of E star. Think of it as 0 is the same as log 1. Base doesn't matter. That's something that we know. And then E star is the same as log E triangle, etc. So I'm not going to repeat. So here we would need to take logarithm of minus infinity kind of to make this work, but we rejected this classical meaning for minus infinity for now. So this is the identity elements, and we can like map them from space to space with log and exp function. Okay, let's move on. Let's consider dual operation for tilde. So in our standard procedure for dual operations, we just consider that operation without head is just kind of a standard operation. So 0 tilde 0 with head on top is 1, we know that. What is 0 tilde 0 with head on the bottom? Let's recall the recursion we built was using this identity that I think it could be equivalent to distributive law, but I don't know that yet for sure. So I just use it as is. So we had something like this, but for different operations. And we wanted it to be 0 plus 0. Left 0 and right 0 here, I could replace them on A and B. Then you maybe would recognize something like we had in the past. A plus B multiplied by A plus B equal A multiplied by B. That's we had it in the previous videos. Okay. So now we use the same for plus and for tilde. So what we have here, this is 0. 1 second. Here clearly we got 1 plus something equals 0. So we have to define minus 1 as a new element in our algebra. So finally we got to negative numbers in our ladder of algebras. So we can write here that this is minus 1. Let's compute more numbers, a little bit more numbers. Let's say minus 1 tilde, dual tilde, minus 1. It is equal to. So another thing that I want to mention, if you remember, we used thing like when we define a dual multiplication, what we did is that we took 2 to the power log 2a. We defined it in terms of dual plus. Here we can do the same. So a dual b, we can define it as log 2 to the power a plus 2 to the power b. This is dual. Okay, that's same thing that we did in the past. So in this case, minus 1 will be equal to log 2 1/2 plus 1/2. So we add denominators and share a numerator. It's 1/4 here. So it's minus 2 as the result. Let's say minus 2 tilde dual minus 2 equal log 2 1/4 plus 1/4. It's 1/8 here, so it will be minus 3. So if you remember dual operation and standard operation, all these were similar to each other. Here we have the same. When we add 2 tilde 2, we got 3. when we add -2 with -2 in a tilde sense, we got -3. So this tilde operation with hat on top, it counts up. And when we have tilde dual, it kind of counts down. For example, if we take 3 tilde dual 3, I expect it to be equal to 2 because we count down. Let's check the computation. It's 8 plus 8. We have 4 here, so it equal to 2. Okay? Okay, let's move on to the next topic. And this is distributive law. We know distributive law for plus and multiply. We checked it for multiply and triangle. Let's just check that it also works for tilde and plus. Like, let me just put it this way. So this is the equation that we want to check. I want to remind you that plus here is stronger operation than tilde, so we don't need parentheses here, but I put them. So let's compute what this equals 4, this equals 6, this is equal to log 2, 2 to the power 4 plus 2 to the power 6, and we can compute that this is equal to 4 plus log 2 5. Here we have log 2, this is equal 2 to the power 2 plus 2 to the power 4 plus 2. This is equal to 2 plus log 2 5 plus 2. So these two are equal. So distributive law works. I do not prove it in general, but you can do it yourself. I think it works. And yeah, that's another interesting property of this operation. Let's move to application. So I will talk about application of this operation, tilde, and the topic will be probability theory. So in probability theory we consider events and we consider probabilities of these events, and we consider combinations of events and the probability of those combinations. So in particular, if we have two events, event 1 and event 2, and we have a probability of happening for event 1, let's denote it as P1, and we have a probability for another event as P2, then we can consider another event, like event that event 1 happened and event 2 happened, and usually we figure out if events are independent, that is just P1 multiplied by P2. And we also consider things like probability of event 1 or event 2 happens, and if they are mutually exclusive, for example, so they cannot happen together, then this will be equal P1 plus P2. Why I talked about machine learning in the past is that when people compute probabilities, for example, for large language models or some other, let's say, hidden Markov models, we have events, not two events, we have so many events. We can get products like P1 multiplied P2, and these products can go like P100 or 1000, and we can sum such big products together, and there's a huge formulas in terms of number of these events. And to make all that numerically stable and sometimes even more efficient for computation, so that float point arithmetic work, instead of multiplying them and summing them, we go into log space. So in log space we have terms like log probability or log likelihood. It means basically that instead of P1 multiplying on P2, we would sum their logarithms. Okay? So for this, let's introduce a new notation. P1 will be log P1 and P2 will be log P2. And also we replace multiplication with addition. So now if we want to compute probability of combined event, let's say probability, but also in log space, right? So we want to take probability of event and event 2 in log space. So this will be equal to log P1 multiplied by P2. This will be equal to P1 plus P2. If we want to compute log of a sum or event 2, we need to go to log of P1 plus P2. And this is equal to log P1 is exponent of P1 plus exponent of P2. So you can recognize here already that this is P1 tilde P2. So clearly, when we shifted from multiplication to addition, addition should shift somewhere as well. And we didn't have a name for this operation, and I say that this is hypo operation tilde, and we just defined it in this video. So plus will shift to tilde operation. Okay, so if you are a machine learning engineer and you use Python packages to train neural nets or do machine learning computation, PyTorch, for example, will have a function called it will be called log sum exp. So this function is nothing more than tilde operation. Okay, so this is just one example, one use case. So in the next video I will try to cover the topic of identity elements and probably dual identity elements. If you remember, we had zero and dual zero, infinity and dual infinity for plus. We'll try to consider all these like concepts for multiplication, for triangular operation, for square, for tilde, for sharp, and we will try to understand how we choose the base for logarithms, how we choose those identity elements. Yeah, that will be the topic of next video. For now, this is it. Please like my video and subscribe to my channel. Its name is Akumath Musings. Goodbye.